Hello, everybody. I hope you can hear me well, right?
We can hear you well.
I'm Alex Kurapov, and I have to thank Eric Fredriksson for bringing my attention to this problem some time ago. And thanks to Parker McCready for being a collaborator and actually encouraging me to do something on bottom pressure for this meeting. What I have had is this 2-kilometer resolution model, which is based on ROMS, Regional Ocean Modeling System. This is a kind of model that's particularly convenient. It does good prediction for processes on a 2-kilometer scale larger, let's say. This is a three-dimensional model, so it gives you the prediction for sea surface height, temperature, salinity, horizontal currents. We used 40 vertical terrain following levels. The domain goes from somewhere like almost Baja California, tip of Baja California, to British Columbia, includes the entire west coast of the United States. We apply forcing to this model, the winds, heat, and freshwater fluxes, some large river discharges in this area in Oregon, Washington. Boundary conditions provide forcing for tidal and non-tidal constituents. So this model does have tides. What we don't have in this model is we don't apply the atmospheric time and space variable atmospheric forcing at the surface. So basically, whatever our results are from the model, you may think that an inverse barometer already taken out. We don't do any data simulation inside. It's not a state estimate. It's a free running model, so it is as good as the model itself. And we actually we submitted the paper that describes numerous comparisons along the coast. Pretty good model from my standpoint. It is a continuous run from 2008 to 2018, and notably it does include the heat wave period of 2014-16, which will be the focus of my presentation. Since it's a long model run and high resolution, we have to deal with the daily average outputs. Daily average is not ideal for removing tides, so we have to do pretty long time filtering for analysis, like 90 days. So what I'm going to show by the end of my presentation is just the model estimates at those locations, which are locations of the pressure, bottom pressure sensors from the OOI, Ocean Observing Initiative network, from inner shelf to mid shelf, slope, and offshore. So how we compute bottom pressure from the model fields like that. So we take the in situ density and split it into the reference density and the deviation, which is fraction of percent, right, or about 1% of that number. So and that would split into the contribution from sea surface height and density. And sometimes they call it baroclinic, but it's not always baroclinic. So basically, if you have if you're in shallow water and your water column is well mixed, but your density, average density in the water column is still different from the reference, you still get a non-zero contribution from this one, right? So what oceanic processes influence bottom pressure? A lot of those were mentioned already. Of course, tides, there are internal tidal motions as well. So guys who are trying to get geodesic signal try to remove those by filtering. So wind-driven upwelling along the west coast. What is that? I think Parker is going to talk more about that. But when the winds blow from the north to south, which happens more often in summer, you have depression of sea surface height and upwelling of the density surfaces closer to the surface. So basically, in this case, those two mechanisms work. Those two parts of the bottom pressure try to kind of cancel each other. Downwelling is about opposite of that. We also have surface-subsurface eddies. We have the slope undercurrent that develops each summer on a slope along the coast, goes to the north. It also changes the structure of the isopycnal slopes. Coastal trap waves. Thanks, Ken, for bringing this topic. Also, whatever propagates fastest, coastal trap waves would start moving offshore slowly as Rossby waves that also may contribute. Also, both for sea surface height and density fields. And there are global or basin scale patterns that influence variability along the coast from time to time, including El Nino. So what is El Nino? So basically, what I'm going to show you is how El Nino anomalies show up in those two parts of the bottom pressure, from in the eyes of the model at least. So I'm talking about 14-16 heat wave. It's not just like the El Ninos when the things came together and made life for biology pretty tough along the west, in all of Northeast Pacific actually, and Alaska. So we had a warm blob arriving, just like lighter water arriving from offshore toward the coast, and that happens in winter 13-14, and then by summer 2014 we had the El Nino breaking through, and the El Nino signal comes as a higher sea surface height and downwelling motion on a slope, and comes as a basically part of that signal propagates as coastal trap waves, if you like. At least that's how I see it. All right, and the picture here shows the anomalies, in the seasonal anomalies in sea surface temperature and satellite in the model, and you see that the model reproduces those quite well, even without any assimilation of sea surface temperature from satellites. So coastal sea level, as I told you, because of the El Nino, it gets elevated by how much? Sometimes 15 centimeters compared to the seasonal cycle. What is shown here is I applied the 90-day half amplitude low pass filter to the daily average sea surface height fields, and this is for two locations of Oregon and in San Diego, California. And I extract the seasonal cycle, the annual cycle. This is the thin line, and the thick line is the actual signal, but low pass filtered. So basically, the shaded areas are where your sea surface height has a positive anomaly, which happens in South Beach, Oregon, of Newport in winter 2014-16. This is the El Nino signal. There's also this little kick is what they used to call moderate or weak El Nino 2009 of 2010. This was driven mostly by the enhanced winds. And this is driven mostly by the oceanic influence, by propagating waves, I would say. In La Jolla, we have the same thing. Remarkably, that peak happens earlier by a lot, like by a few months. So if this is the signature of the propagating signal, that would come actually propagate pretty slow. That's again, I'm saying that for you, but maybe you'll try to understand it in terms of slowly propagating very long waves. At least will help me understand it. So yeah, so anyway, the sea surface height is depressed. So the sea surface height is elevated, and because of the El Nino, the isopycnal surfaces, the surfaces of constant pressure, are depressed down. So how does the bottom pressure computation look like for very close to the coast, 26 meters? So we have, so the red line here is the total bottom pressure. The orange line is contribution from sea surface height, and the blue line is contribution from the density. So basically, there's no compensation between those two terms in very shallow water. So basically, we have about like 15 centimeters of water level anomaly because of the El Nino here. If you go further offshore, there is a partial compensation of the density component. So basically, but still the total bottom pressure is strongly anomalous because of the El Nino. As soon as you go off to the shelf break, remarkably, there is still large sea surface height contribution to the anomaly, but it's almost totally compensated by the density part. And even if you go further offshore, you still have the same pattern. So whenever you have anomaly in sea surface height, it's very well compensated in deep water by the density part, which kind of funny thing, right? So, and I'll stop here and take a question so you can read the summary.